I have this chat open in the background, so if you guys have any questions, you can post it in the chat. Okay, so nothing to worry. And I think everybody can see my screen, right? Can you put yes if you can see my screen? Can you guys see my screen? Just put yes. Okay, thank you. Okay. Yeah, today, so we are having the day school 3 of EEX3331. In this day school, I'm going to cover measurement of earth resistivity and magnetic measurements and sensitivity of bridges. So I know the book we have provided to you is very well explained on these things. So I will give you a push up for these things so you guys can catch up. Okay. So first, we are going to talk about measurement of earth resistivity. So this is a place where many of you have got confused. You guys have sent me a lot of questions on this because people have confused with resistivity and resistance. You will see what we are going to discuss in this session. So in this session, we are going to see how we can measure earth resistivity and how we can measure earth resistance. Actually, so you know this subject is measurement and instrumentation, but when it comes to earth resistivity or any parameter usually related to earth, we cannot measure accurately. We are going to estimate it approximately. Okay, so we are going to see several methods which we are going to use to measure this resistivity and resistance, and we are going to see how these methods work. Okay, first we need to know what is earth resistivity. So usually earth resistivity is a measure to indicate how much the soil resists conduct electrical current. So this is a very easy explanation. We are just going to have a measure in which how this soil is going to resist to conduct electrical current. And this measurement is usually expressed in ohm centimeters. And when it comes to soil, so you know soil in your house is different from the soil you find in open university premises, right? So that is not the only you can also visually observe the soil type is somewhat difficult when you are going to various places. So these places also have different resistivities. So each and every soil will have different resistivities. And as I mentioned earlier, we cannot measure this resistivity accurately. So what we do is we give a value as a range. So if you see the ranges I have given here, you can see how wide these ranges are. See, so for surface soil, our resistivity can change from 100 ohm centimeters to 5000 ohm centimeters. So that is a very large range. See, so therefore we cannot exactly say this surface soil will have this much resistivity. And also when it comes to clay, it can go up to about 10,000 ohm centimeters. And surface limestones, it is around 1 million ohm centimeters at the high side. So this is how soil resistivity changes. So you guys can get the idea. The soil resistivity is not a fixed thing. And now you guys might be wondering, why as electrical engineers we need the soil resistivity? So usually these things are usually, you know, environmental engineering, somewhat civil engineering kind of things. So why do we need this soil resistivity value? So main requirement to need to know the soil resistivity is to determine the location of plugging in your earth rod. So you guys are going to the industry, so then your boss asks you to find the best location to plug your earth rod. So what you are going to do is you are going to have the earth resistivity measured in several places, and you are going to select the lowest earth resistivity available place. But you have to consider about other things also. So some maybe it can be some somewhat wet place. So you are not going to plug your earth electrode in a place like this, because there can be other considerations like eroding and stuff. So the main requirement is to determine the location of plugging your earth rod. That is the main requirement of knowing the soil resistivity value. So in this subject, we are going to talk about two methods of measuring earth resistivity. So this is where some people get confused. So we have several methods. So some people can't like remember, or like not remember, actually they can't understand why we have two methods to like several methods to measure resistivity and also resistance. So when it comes to earth resistivity, we are going to have two methods. The first one is Wenner method, and the second one is, so some people call this Schlumberger method, some people call it Schlumberger method. So either way is fine. So you can use any term. So I'm going to refer to it as Schlumberger method. So we have two methods. We are going to discuss both of the methods in this session. So we'll see how these methods can be used to measure earth resistivity. So when it comes to Wenner method, we have a configuration like this. So in here, you have four electrodes arranged in a equal distance to each other. So you have a voltmeter connected to the inner electrodes, and you have a ammeter connected to outer electrodes. So what we can measure here is voltage and current. So if you can measure voltage and current, you can determine the resistance value, right? But we are not going to take this as the earth resistance. But here, so remember, we are going to measure resistivity. So we have to come up with a equation which we can convert this resistance value to resistivity. And don't get confused. The resistance value you measure here is not the earth resistance. This is just the resistance between these electrodes. So this Wenner, the scientist, has come up with this equation. So you can use this equation to determine the earth resistivity. So when you're looking at the equation is somewhat uh, complex. To minimize the complexity, what we do is we take this distance between electrons very larger than the depth. So when you take it like this, what happens is this value becomes 2 and this value becomes 1. So your numerator will be 2 and 4 5a r over 2 will be equal to 25ar. So we can simplify our equation by having these electrodes arranged in a wider way. So we have this equation. We are not going to discuss about how you can prove this equation, which is out of your scope. So you guys can read more information on this Wenner method also. So this is included in your textbook given, and I have covered many things here. So there are some additional stuff there also. So you read them. And to get understanding of this equation, we'll do a small calculation how you can answer a question when it is given to you in the exam. So we have a simple exercise. So we have a Wenner configuration. we have used Wenner configuration to measure earth resistivity. So the electrodes are spaced uh, 5 meters, and electrode depth is 0.3 meters, and measured voltage is 97.5 volts, and measured current is 1.25 amperes. So we'll see how we can work out this problem. So first, let's write down the equation. So we have rho equals 25 AR. So in here you can okay, I will give you a rule of thumb. So if your A is larger than 10 times B, you can use this equation. If your A is somewhat closer to B, so not equal actually, not very much larger, A is not very large compared to B, you have to go with the complex form, the complex equation. So I will write it down here. So in here we'll see what is our 10 times B value. So 10 times B value is 3 meters, right? So our A is larger than 3 meters, so we can use this equation. So let's use this equation and calculate rho. So rho will be 2 into 5 into A is 5 meters, and your R you can easily calculate using 97.5 over 1.25. So please remember the units you have applied here. So this is in meters, and this will be ohm. So this will come from ohm meters. So usually we express our resistivity in ohm centimeters. So let's do the calculation in ohm meters and convert it to ohm centimeters. How we can convert it to ohm centimeters? We just multiply it by 100. So after doing this calculation, you will get 2,450 meters. So that means, so you can easily convert it to ohm centimeters. So you know, so you have to apply centimeters here. So just multiply it by 100, convert it to ohm centimeters. So that's how you do the calculation using Wenner method. Now we are going to talk about this Schlumberger method. So actually this Wenner method is very old. So this Wenner method is introduced in I think in 1900s, closer to 1900. So this Schlumberger method is introduced after 100 years. So this is actually a just an advancement of Wenner method, but it took very large time to emerge. So in here, what we do is we have the same configuration, but we have different electrode distances. So what is important here is the inner electrodes are fixed. So these electrodes are fixed. So these ones are fixed. And we only move these two. Okay, I forgot to tell you. So when you are taking this earth resistivity measurements, what you can do is, so we are not going to plug these four in a single place and take measurements. So what we do is we usually define an array like this, and you plug your electrodes in an array. So you map a whole region for earth resistivity. So So if you use Wenner method, you need 4 person to move these electrodes and another person to take measurements. But when it comes to this Schlumberger method, your inner electrodes are fixed and you can vary the distance between other two. So what you do is you keep these two fixed and you move this in this direction. So you can cover more ground in horizontal way. So if you need to move it in a vertical way, you have to move these two also. But usually when it comes to Wenner method, you have to move all 4 electrodes. But when it comes to Schlumberger method, you only move outer electrode. So we only need 3 persons to 2 can change the electrode locations and 1 can make measurements. So that is the advantage of this Schlumberger method. You have an uh, advantage on measuring, uh, advantage on, actually on workforce. So I have a question: is it necessary to set the linear array? So I think you're asking about the setting it on linear region, right? So are you asking about this? Is like setting it on in this form or taking measurements in a linear array? Okay, anyway. So actually it is necessary because uh, these equations these equations are proven based on, like, they assume these things are in a linear array. That's why you need to keep them plugged in a linear configuration. Okay, so we have example. So in here we have to use this Schlumberger method and do example. So we have electrode spacing voltage probes, which is the fixed one. So this is fixed as 2 meters. Electrode is spacing voltage and current probes. So that means, so if you have uh, voltage probes like this, your current probe like this. So this is C and this is A. So our equation, we have only single equation this time. Yes. So now we have the equation here, so we can easily do the question. So we can easily calculate rho using the given values. So you know phi is a constant, C is 6, and again you have a 6 and 2, and your R will be 106.5 over 1.25, and A is 2. So in this case, you will get the answer as 6,423.92 ohm meters. So you know how to convert it to ohm centimeters, right? So work several examples at home, so you guys can get the understanding. Okay. So now we know what are the methods we can use to measure earth resistivity. So now we have discussed about earth resistivity, and we have 2 methods. We are not going to discuss in very much in depth. We have Wenner method and Schlumberger method. So we have done 2 exercises using those 2 methods. So now we are coming to earth resistance measurement. So first we need to know what is earth resistance, and we are going to discuss about what are the measuring methods we can use to measure earth resistance. So you know earth is a very large and not a homogeneous body. Therefore, we cannot actually define an absolute resistance to Earth. So what we are going to do here is we are going to measure. Actually, measure term is a little bit wrong. As I explained here, we are going to estimate the resistance observed by the earth electrode. So earth electrode means, so you know your house has a earth electrode. So this, when you are injecting a current through this earth electrode, it will observe some resistance. So that's what we are going to measure here. So sometimes people are getting like somewhat confused with how this earth can have a resistivity, how current flows through earth. So still you guys are level 3 students. So when you are coming to level 5, you are going to do a subject called electrical installations. So you are going to talk about ground returns. So in there you have a current flowing through ground and completing a circuit. In the transformer you have in your substation or the transformer pole you have next to your home, and you have a ground there, and your house has a ground there. So there's a ground return to the ground. So we are going to discuss about these things. So some people get confused. So usually when we test soil, we cannot see any current flowing through the ground. So how this ground can conduct electricity. So and also you will learn in the level 4 and 6, no, level 5 and 6, this earth resistance is a very low value. So earth resistance, usually they say keep it under 10 ohms, 20 ohms. Usually in industry, we are trying to obtain a 10 ohm earth resistance. So how that earth can have that much lower earth, that much lower resistance and or high conductivity? So the explanation is a bit simple. What happens is, our, this is the expression for resistance, right? So resistance, it is resistivity. So if you take a rod or something like this, the resistance of this will be, this is L, and the material has a resistivity of rho, and this surface is A. So the resistance of this will be rho L over A. So now when you plug the earth electrode into ground, so you have some soil contacting your earth electrode. So what we do is we have several layers of this. So what we do is we assume the earth is made out of layers. So if you consider this first layer, this first portion of soil, the resistance resistance added by this first layer. So after considering the soil as a layered thing, what we do is, so this one has R1 resistance, so this one will have R2 resistance, R3, R4, and go on. So this one will also have a resistance. So what will but see, the length is somewhat same, right? If you take the layers as arranged like this. If now consider, so this one will add some resistance. Let's say it is R1. So this second layer will add some resistance, R2. The third layer will add some resistance, R3. So going on and on. So what will happen is, so if you, let's assume we have a constant rho and constant L. So rho L. So this we have A1. So A1 will be the shape, the area of the shape. So this is something like a cylinder. But this is this is something like a can. You can observe the shape is like a can. So you have some area to it. So this area is somewhat small. So then you come to the second position, A2. A3. So you can develop the model something like this. So what happens is, so this A is getting larger and larger. So the area of this can is large, small. This one is little bit larger than that. This one is little bit more larger. And when it comes to somewhat here, the area of this can will be very much larger. So when your area is very much larger, what will happen? The resistance value will be lower. So in the first portion, the first volume of soil will add a critical amount of resistance to the earth resistance. But after going several layers, it will add a negligible resistance. So what we say is, so your resistance will increase something like this. So it will increase to a point where your A is considerably larger and your R is very low. So in this point, it will reach something like a flat curve. So this is called plateau. So this point is called plateau. So that's how your earth resistance will build up around your electrode. So I hope everybody now can understand how this earth resistance is modeled. So when you're coming to measuring this earth electrode, you have two methods. The first one is fall of potential method, which is a very accurate one, and the second one is the dead earth method. Okay. So now we are going to talk about this fall of potential method. So fall of potential method, it is using the concept I explained earlier. So what we do is we have three electrodes. The rod one is your earth electrode. The earth electrode means the earth electrode of your building. Then you have a potential electrode. So actually this is a bit wrong. So this has to be rod 3 because the nomenclature given. Okay. This is rod 2. This is rod 3. So we have rod 1, rod 2, and rod 3. Rod 2 is a potential electrode. Rod 3 is a current electrode. So what we assume is, we assume our plateau. So this flat thing is called plateau. So plateau is reached when you are going 62% of the total distance of these two electrodes. So usually these two electrodes are distance more than 10 meters. So after going 62%, that means 6.2 meters. You assume you have found the location of the plateau. So what we do is we measure the voltage and current of the meter. So in this session, we are not going to see the most important details of this fall of potential method because it is not covered in this syllabus. It is also mentioned in your book also. So your meter will give you voltage and current measurements, or sometimes it will automatically give you the resistance observed by your earth electrode. So it's very easy to do. And what you have to know, you only have to know is you have to connect your rod 1 is the earth electrode. You have to connect your rod 2 approximately at 62% of the total distance, and rod 3. So you have to connect rod 3 first, then you have to adjust rod 2 to 62% line, 62% point. So At there, we assume we have reached the point we can take a correct measurement of the earth resistance. And that's the follow-up potential method. So read the things given in your book. So actually this the derivation of equations and these things are not discussed under your level of in your level. You will discuss this in the level 5 in electrical installation subject. So we are just going to know how we can measure the earth resistance. And we have another method. This is actually a very easy to understand method. This is called 2-point method. In here, you only have 2 points. The first one is your earth electrode, and second one is usually place where in distance ground. So what you do is you measure the resistance between your earth electrode and that point. So you will get a value, and this is just a, so in here this earth resistance tester is just a resistance measuring equipment. So what it do is it simply measure the resistance between these 2 points. So the accuracy is very low when it comes to this method. Okay. So that's all we need to know in earth resistivity and earth resistance measurement. So read the book also so you can understand more on those things. And now we are coming to a bit important part, magnetic measurements. So in here we are going to measure, usually we are going to measure 2 or more parameters. We are going to discuss those things in the upcoming slides. So first thing we are going to measure is flux density. So I have included the definition of flux density. So it is usually the quantity of magnetic flux lines pass through a unit surface area. So this is measured using Weber per square meter, and you can also measure this in Tesla. So this is here. This is actually quantity of magnetic flux lines. Okay, so there are several methods of measuring this flux density. The first and most important one we are going to discuss here is Hall effect method, and we also have Gauss meter method and bismuth material and mu metal wires. So actually in this session we are going to discuss about this, the Hall effect method, which is the most important thing, and there are a lot of details available in about this method in your textbook also. Other ones are also included, but with only slide details. So we are going to talk about this Hall effect in detail here. Okay, I'm getting some questions regarding Cat 2. I will address that in the end. Okay. So first we'll see what is this Hall effect. So when it comes to Hall effect, what happens is, so the main purpose here is to measure the magnetic flux. So we have a magnetic flux oriented in a way, in a direction. So what we do to measure it is, we have a Hall effect material or a conductive material, which we know the Hall effect coefficient. So Hall effect coefficient is a constant to that material. And so when it comes to here, so you can see your flux lines are going like this, and you have your Hall effect material like this. So this Hall effect material is applied with the known current in a direction. So if your flux line is in this direction, you have two perpendicular surfaces. You apply a current into one surface. As a way, it goes like this. So your current is flowing in this direction and your flux is oriented in this direction. So you have another two phases left, right? So in Hall effect, what it happens is there will be an induced EMF across these remaining phases. So according to the equations or the theory, the what it says is the induced electromotive force or the EMF or the voltage is proportional to the current flowing through, and it is also proportional to the magnetic flux. So when we are, so in here, our unknown component is magnetic flux. We can apply a known current to this material and we can measure the induced EMF. So after measuring this, we have this equation. So RH is the our Hall effect coefficient of the material, and I we know, and D is the thickness of this phase, the width of this phase, and we can easily readjust this equation in this way to calculate the flux density. So you can calculate flux density, you know the current, and you know all the dimensions of this material, and you can easily calculate the flux density. And so now we are going to talk about somewhat important topic, which is BH curve. When it comes to magnetic measurements, we have this thing called BH curve. So what it does is it gives an idea about how these materials, each material, so each materials will house different permeabilities, and they respond differently to applied electromagnetic, external magnetic, not electromagnetic, external magnetic fields. So this BH curve, it plots the flux density against the magnetic field strength. So in here, so when it comes to this magnetic material, there's a special phenomena called hysteresis. So yeah, before going into that, you need to know this equation. I think this you have learned in your advanced levels also. So in here, this is flux density, and this is your magnetic field strength. So when it comes to magnetic materials, so you have this special phenomena called hysteresis. So people get, you know, uh, like scared of these additional words we used in electrical engineering. So what it means simply is it lags in response. So this is something like this. So let's say you are driving a vehicle. So you push your accelerator to a to the lower point of your car. So you press it very hard. Your car will not accelerate to your top speed suddenly, right? So it will come to your top speed in a slower phase. So you can push your leg very hard and very in a high speed, but your car will respond according to its capacity. So the engine will respond as its power output. So it will come to the speed you are intended to by pushing the pedal. So it is something like this. So when you apply your magnetic field resistance to your material, your flux density will not automatically come to the desired position in a in a sudden phase. So it will go there slowly. So this is called hysteresis. And also because of this hysteresis, the magnetization characteristics. Okay, remember this. So this is magnetization. So this equation is a linear equation, but to achieve this is point, the operating point, it takes some time. So it is not linear. So magnetization is not linear. So the magnetization will take some time and it is not linear. And there will be some saturations of the magnetic material also. So if you the saturation point means if you put a very high magnetic field strength to your material, it will go up to a flux density and it will stay there. So it will not go above that value even if you have a very high magnetic field strength exposed to the material. So that is called saturation point. And due to these characteristics, so I said that your operating point or the final value will reach slowly in a slow phase. So in that case, there will be something called hysteresis loop. So this means, so I will explain it in by showing the curve. So you increase your flux intensity, the flux strength, the field in strength to a very high value, it will come slowly there. Then you reduce it to some value. So it will not go in the same path it followed. It go in a somewhat different path. So this is called, so because of this characteristic, it will form a hysteresis loop. So you need to know about this phenomena also. So now, so we know there's this thing, and we need to determine this BH curve. So we have a apparatus like this to determine the BH curve. So what we can do here is we have a specimen. So we are going to measure the flux density through this specimen, and you have applied your field through this coil. So this coil is wound around this specimen, and you are taking another coil out of this specimen to measure the flux using a galvanometer. So in here, what we can do is we have uh, a potentiometer. We connect this main winding into the first position of the potentiometer, and we apply a small magnetic field and we take the measurement. So we measure flux density using this apparatus. So then we are going toward the higher values accordingly. So when you are doing this, you should not keep it disconnected for a long time, because if you observe the flux curve, so when you increase it to some value, if you uh, reduce this h, it will go to another operating position. So when you are again applying the force, it will follow another path. So there will be some errors when you are mapping this BH curve. So when you are doing this, you have to do it quickly by connecting these points in a incremental manner. So you cannot connect 1, 4, 5 like that. You have to go in the correct order. And you can also come back in the reverse to measure the reverse curve. So in the forward curve, it will be something like this. And in the reverse curve, it will be something like this. And that's everything you need to know about this BH curves. So now we are going to talk about this iron losses. So earlier we talked about this hysteresis, and we have something else called eddy currents. So eddy currents are usually they only occur when your magnetic material is connected to a AC supply. So, but when you are measuring your BH curve, you use a DC supply. So these things can uh, vary according to your supply. So in real world, so we cannot use use these measurements we took use in this DC measurement to design our appliances to the AC measurement. So transformers, on those things we have a BH curve. We have to know the correct BH curve to design those things. So we need to have some other measurements. So we have some other more advanced methods of developing the BH curve using oscilloscopes and stuff. So you have those things included in your lecture, the provided materials. Please read them so you will understand. And I'm not going to discuss these things in this session. So please go through the notes and understand them. And they are very easily explained, so you can easily understand. And now we are going to see how we can measure the iron loss. So iron loss, we are going to measure the iron loss, we are going to simply use a bridge. So this is this is called Maxwell bridge. So I'm not going to discuss how we can derive the equations to bridges, because in the last I think in the last session we derived many equations for bridges. So this is similar. So you have to take the balance condition, and finally you will arrive at uh, measurement, the arrive at equations to determine the iron loss component. So in here, this is connected to AC source. So we can measure the iron loss. So when you are connected to DC source, you will not have this eddy current. So iron loss will not be the eddy current loss will not be there. So you cannot calculate total iron losses, because the iron losses will include this hysteresis losses and also eddy current losses. So these are also called core losses. Okay, and so in here we have the equation to derive iron loss. So go through the material and you will understand how we can how you guys can arrive at this equation to calculate the iron loss. As I as I mentioned earlier, today's session is not a very big session. I'm just going to give you a simple push-up to go with the subject, so you guys can understand. So these things are explained very well in your book, so you guys can easily read and understand. Okay. So in here we are going to start the sensitivity section. So sensitivity is defined as the variation of the detector current for a small variation in the variable arm near the balance condition. So what we do here is we are going to observe the variation of the detector current. So in a bridge you have your four arms, and you have your detector here. So this is called detector. So at the balance condition, your detector current is 0. So what we are in this session, what we are going to do is we are going to develop a relationship between this variation of detector and your variable arm. So you have a variable arm somewhere. So I'm just going to give you the concept of this sensitivity, and you can like uh, like go on with it and get the idea how to define expression for a sensitivity expression for a bridge. Okay, so let's identify the concept. So as I explained before, in here we are trying to develop a relationship between change in detector and change in variable arm. So here you have detector and here you have variable arm. So let's see how we can, uh, let's give me 2 minutes. Okay. So in here, we are trying to develop a relationship between the change in detector and change in variable arm. So let's see how we can derive the sensitivity relationship. And here, our detector parameter is voltage. So in here, so we are going to develop a relationship between this voltage and this Z2. So this is the variable component. So the sensitivity expression will be given by the partial derivative of our detector parameter by the our variable arm parameter. So this can be impedance, so if it is DC, this is just resistance. So this is the basic idea or the concept of deriving a sensitivity equation. So let's try how we can derive expression for this bridge. So first we have to derive an expression for V, or the voltage across these 2 points. So you know we have our E across these 2 points. If you take voltage division and find out voltages in these 2 points, you can arrive at a expression like this. So this will give you the voltage at this point. So this, let's say it as V dash and this is V double dash. So it will give something like this. So your detector parameter voltage is defined. So you can also simplify this using not simplify actually. You can have it in the same some other form like this. So now, so first step one is like you have to derive the expression for your detector parameter, and step two, you have to take the partial derivative of it with the variable component. So very easy. So see, so you have your expression here. You just take the partial derivative of it using this variable arm coefficient. So after taking the coefficient, so you will end up with something like this. But you may remember sensitivity is the you have to develop a expression, but it is near the balance condition. See, so this phase is bit involved. So when it comes to here, near balance condition, you know this expression will come true. So this is simply Z1 over Z2 equals Z2 over Z4. So you know in balance, this is the balance condition. So from this you can derive this equation. So we have this component right here. So at near balance, so very near balance, this component will go to 0. So you will only end up with this component. Okay. So that is the concept of uh, developing expression for sensitivity. So I have to mention something. Actually, one of your students pointed out to me. So in the lecture note, uh, there's something wrong in the equations given there. So this 2 or the square is missing. So when you are reading this part at your home, you can, so please remember this, there's a 2 missing in your textbook. Okay, so you can actually do this. This is very easy. So you know partial derivatives. So just take the partial derivative of this v from so, so I know you have read all of these things because you have already submitted TMA3. I'm now in the process of grading TMA2 and your TMA1. I have missed several TMA1s. So I will update the results of them in upcoming 2-3 days. So you guys can have a look at your marks. And so now, so our presentation is over. So as I said before, today is a very small session. So I needed to cover these things. So for the CAT 2, I will put so you remember in last time also I gave you guidelines on CAT 1, right? So CAT 1 was not prepared by me, it was prepared by the previous coordinator. So CAT 2 I will be preparing. So you have I think it is the last subject you have in the timetable. So I was busy preparing CATs for other subjects that I'm doing. So for this I'm starting to prepare the CAT in tomorrow morning. So I will by the tomorrow evening, I will be able to give you a guideline on how to study for the CAT 2 and what other things you have to uh, concern mostly on. Okay, so that's it. So if you have any questions regarding things like CAT 2, I can't answer now because I have not made the CAT 2 yet. So I will be preparing it tomorrow. So tomorrow evening, I will upload a guideline to your LMS. Okay. So that's it. So there are several other things I didn't touch in this day school. So you have the book and it is very easily explained. So and so you guys can go through the notes and understand. And people are asking the CAT to the assignment 2 answers, right? So assignment 2, yes, CAT 2 is you have 1 month, right? So probably yes, I can give you marks before your CAT 2. And is it a MCQ or it not? It is similar to the last time. So I will be giving the paper. You have to answer it in a paper or a book, and you have to take pictures, and you know the drill, right? So last time you used these apps called like CamScan and all, and upload. And in this time, as I don't know whether this is correct or not. In this time, I will be just giving you the paper, and there will be only Google Drive. I don't know this is exactly correct, but I had several problems last time because some of your students have not activated your OUSL email. So before, like without activating it, you cannot access the Google form. So please activate it right away. So if you don't know how to activate it, ask from someone who knows. It is, I think it is just you have to go to Google Gmail web page and type your email address, and your password is your NIC number, as I know. So then it will automatically activate. So last time I had a case that some student has not activated the account, so she couldn't uh, log in. As I have lost my phone, I can't log into that. Okay, so then there will be a problem. Actually, I am not very sure about this thing, but I heard this this time the server is like not capable of handling this much submissions, and they are only allowing Google Drive, Google Form. So I will tell this to Dr. Uday Kumar. So maybe so I know that our IT people have access to your accounts, right? So they will be able to reset the password for you. So maybe something like that uh, can be done. Okay. And I usually like cat to the question paper, the format will be, there will be two questions. Mostly I will only stick to two sections of the books, and since I did the this day school 3 today, I may not be giving questions from day school 3, probably from day school 2. We'll see. Okay, so there are several remaining sections we can ask questions from. So anyway, I will be putting a notice on the LMS so you guys can go through the materials. And the other thing, like, please like activate your accounts. Okay, the Gmail, not go to Gmail and put your OU email address and activate it. So otherwise you will not be able to submit those submissions. Uh, this is actually just a uh, just a news that I heard. Still, I don't know whether it is like true or not. The thing is, like, our server is not capable of handling that much submissions. So last time also it did it. I know it did it somehow, but I think the people are complaining that maybe it has some damages or something. I don't know. So that's it. If you have any questions, you can ask, like regarding the cat 2 or other things. I will give you TMA 2 marks before the cat 2. Okay, so don't worry about it. Uh, the things, there's no other things to mention, right? Okay, so if anything, you can put email to me. Uh, uh, you guys still don't have the hard copy book, right? I will also ask about that from the Dr. Uday Kumar. Okay, so he is the moderator of this subject. So he will, I will ask from him. So he might be able to arrange something. I think the problem is with the press, right? So a lot of corona cases, and so they cannot print the materials. I don't know exactly, but we'll see. Okay. Okay. Yes, I will upload. Yes, I will upload. So don't worry. Like before, before the cat 2, I will be uploading everything. Okay. Uh, okay. Thank you. Uh, okay, so then we can stop the session, right? So I wish everybody to work well and do your exams well, and stay safe. Okay. So like, it is the most important thing these days. Stay safe. Okay. Okay. I'm going to finish the session now. Okay. Bye.